The primary results of thin airfoil theory that's useful for the first part of today's lecture is for determining stability. Okay, so thin airfoil theory tells us that the derivative of the lift coefficient with respect to the angle of attack is equal to what? 2 pi, that's right. And last Friday we have seen practically for relatively thick airfoils, the derivative is slightly above 2 pi, right? Maybe 10% more than 2 pi for regular airfoils like 0012. And what is the derivative of Cm with respect to alpha? For thin airfoils, any kind of thin airfoils. At quarter chord. Yeah, if I don't say anything, the moment is going to be around quarter chord. That's right. So what is the derivative of moment coefficient with respect to alpha? It's an answer that's even simpler than this one. 0, that's right. So when I increase the angle of attack, I get an additional pressure delta that's centered around the quarter chord. That means I get no additional moment, right, when I increase my angle of attack. All right. And then another thing we did is define the center of lift, right? The center of lift is defined such that the moment integrating the aerodynamic moment due to pressure of xc minus x delta p x dx would be equal to 0, right? So that's the definition of the center of lift. That is the moment due to the pressure difference on upper and lower surface. Around that point, balances out to exactly 0. And we did a derivation that tells us that xc over c is equal to what? Is equal to a quarter minus cm over cl, right? So that's the result of the derivation. And we analyzed the several cases. For symmetric airfoils, that Cm, according to thin airfoil theory, is equal to 0. So the center of pressure, the center of lift is exactly at quarter chord, right? Okay, so today I'm going to give you 2 questions. One question is use thin airfoil theory approximation, which is the examples above, for how the pressure distribution changes as angle of attack changes to estimate the center of lift for both of these 2 airfoils at a lift coefficient of 0.4 and 0.5. And then particularly, are they stable, right? So first let's answer the first question, right? Estimate the center of lift for both airfoils at these 2 CLs. The first one should be easy, right? So can somebody just think for maybe 10 seconds and think like, how do we know the center of lift for this airfoil at CL equal to 0.4 and 0.5? Yes? Quarter chord? It's the quarter chord, that's right. For a symmetric airfoil with Cm equal to 0, right? We know this is at 0 degree angle of attack, but dCm d alpha equal to 0, right? So the Cm should always stay around 0, no matter what Cl is going to be, right? Cm is equal to 0. So that means according to this formula, xc should always be at the quarter chord. Okay, now a slightly more difficult question is for this airfoil, right? What is the center of lift for this airfoil, knockout 4412 at CL 0.4 and 0.5? That requires just a little bit of calculation. Do you see these numbers? Okay. If not, let me magnify it a little bit more. How do you do the calculation? Anybody tell me the approach you are taking? How are you calculating the center of lift at CL? Because this is I'm giving you the CM at a CL at alpha equal to 0. Yes.
Is it that equation C over 4 minus C over C?
Yes. Use that equation. That's right. That's That's right. Use this equation, and but what is CM and CL? Do you plug in? Yeah, I'm asking you the center of lift at a different angle of attack as what I'm shown over here, right? So what is going to be the CM and CL at that different angle of attack? Specifically, I said at a lift coefficient of 0.4 and 0.5, right? So that should give me two different center of lifts or centers of lift. Yes?
The CM will stay the same, right?
That's right. CM stays the same no matter what angle of attack do I put it on, right? That's right. And the CL is what have I told you, right? 0.4 and 0.5. So let's do the calculation. Anybody have results? Yeah, so for you, okay, just right now, I'm asking you to compute the center of lift for this airfoil at CL equal to 0.4 and CL equal to 0.5, right? And particularly, I want to know how does the center of lift change as I increase my CL by increasing my angle of attack. We already just look at the symmetric airfoil and say that the center of lift doesn't change as I increase my angle of attack. It stays at the quarter chord, right, for a symmetric airfoil. Yes?
So for CL 0.4, I got 0.528, and then for 0.5, I got 0.4224.
All right. Okay. Good. So what you get is that for CL equal to 0.4, you get a XC equal to what? 0.5 something?
0.528.
To 8. And for CL equal to 0.5, you get XC equal to 0.422. Okay, good. So as I increase my angle of attack, yes?
Didn't we just solve for XC over C?
Yes.
Yeah,
that we should always multiply by C on that. That's right. Yeah, thanks. So what we found is that as I increase my CL by increasing angle of attack, my center of lift shifts from downstream of the midcord to upstream of the midcord, right? Let's actually think about the consequence in terms of stability of the airplane. So if this is the only wing I have, okay, if my airplane is designed to fly at CL equal to 0.4, then where should the center of gravity of this airplane be in order for the airplane to fly straight, not doesn't have a moment that like rotates the airplane? Where should be the center of gravity of the airplane if the airplane is designed to fly at this CL? That's the cruise condition.
It should be at the center of lift for that CL.
Yes, it should be the center of lift, which is around this point, right? Okay, so now imagine I get a slight perturbation that just pitches up the airplane a little bit, or get a wind that goes up a little bit, get a gust, right? That increase either way, that gets an increase in the angle of attack, and as a result, increases the CL from here to here, right? So let me just draw. This is the center of gravity. So this is G, okay? And at 0.4, I get a lift also on this point. Now at 0.5, the center of lift is shifted to here, right? So this is lift at 0.5. This is the lift at 0.4. Okay, what happens? what moment do I get on this airplane due to a combination of lift and gravity? Well, we see two things, right? One is the lift now is greater than gravity, so the airplane is going to go up. It's going to accelerate upwards, right? That's the consequence of a gust hitting me or increased angle of attack. But the second consequence is the moment. The lift combined with gravity is going to make the airplane pitch in what way? Pitch up, right? And that is going to further shift the center of lift towards what? Towards the leading edge, and in fact it shifts towards the quarter chord, right? As if you look at the formula, if I keep increasing CL, CM doesn't change, so this thing goes to 0, and my center of lift actually always shifts towards the quarter chord. So it continues to shift the upstream towards the quarter chord, and that increases the moment even more, and makes the airplane pitch up even more. So is that a stable configuration? No, that's unstable. Okay. All right. So that tells us how to analyze stability of airplanes, right? So if, as I increase my angle of attack, the center of lift, if it shifts upstream, then it's unstable. On the other hand, if the center of lift shifts downstream, I get a stable configuration. How about the second question? Estimate the center of lift for both airfoils at CL minus 0.4 and minus 0.5. Right? So that's assuming the airplane is flying upside down. Now, are these airfoils stable? Well, the first question is a non-question because upside down or not, this is symmetric, right? So we get a neutrally stable configuration over here. The center of lift doesn't change. But how about this one? What is the center of lift at minus 0.4 and minus 0.5? Well, I think I can save you the calculation here. The only difference is that the CL would be negative, right? Instead of a positive CL, I get a negative CL. And CM stays exactly the same. CM does not change, whatever angle of attack I have. So basically, that means I'm going to change the sign of the second term, right? So the center of lift is going to be, if I draw the quarter chord as a symmetry point, right? So let's say this is the symmetry point. Then at minus 0.4, my center of lift is going to be pointing over here. So that's the lift at minus 0.4. And at minus 0.5, my center of lift is symmetric to this lift. So that's my lift at minus 0.5. Any questions on why the center of lift is like that? Okay, so I'm just reversing the sign of this term. As a result, the center of lift is basically symmetric to the quarter chord, right? Yes?
Shouldn't you also reverse CM?
Should I also reverse CM? No. The CM stays the same, right? So dCM, d alpha is always going to be equal to 0. So essentially what happens is that CM is negative, right? Which means I get a nose down moment around the quarter chord, no matter whether the lift is positive or negative. Okay, right? So I would reverse CM if I actually make the airfoil upside down, right? In that case, in that case, I would reverse also the direction of these arrows. They would be pointing upwards, right? And so basically here I'm thinking about I still take the frame of the airplane. It's just flying upside down. It's just the gravity is now pointing up, right? Okay. So now let's consider the stability again, right? So first of all, it is completely okay for the center of lift to be outside of the airfoil, right? That's just because the delta P doesn't always have to be positive or negative, right? In this case, if the airplane is flying upside down, then the pressure on the upper and lower side actually reverses during the chord. So that means the center of lift can be outside of the airfoil. And then let's look at if the airplane is flying upside down. It's designed to fly upside down at a CL of -0.4. Then the center of gravity should be here, right? As we have said before, the gravity points upward in this picture. Now, as you, if a gust comes in and increases the angle of attack, so that CL is now, I should say, decrease the angle of attack, so that CL is now -0.5. The combined torque is going to pitch the airplane so that the nose actually goes up, right? And the tail goes down in this frame of reference. That's actually increasing the angle of attack back towards 0, and restore the airplane to a lift coefficient that is closer to 0. So basically, flying upside down, the airplane would be stable. All right. Okay. Or in other words, as I increase the angle of attack, if the lift actually shifts downstream, the airplane is going to be stable. Right. So this is some analyzing the stability of airplanes using thin airfoil theory approximations. Okay. Yes?
With that shape of an airfoil, how would you achieve a negative lift coefficient?
How to achieve a what?
A negative lift coefficient.
For this airfoil, I would achieve a negative lift coefficient if I just pitch down the airfoil so that I have a very negative angle of attack. Yeah. Okay. Right. So basically, if you follow thin airfoil theory, right, DCL d alpha equal to 2 pi, so you can estimate from this. At 0 angle of attack, the CL is 0.5, so you can basically plug into this formula to estimate what negative alpha do you need to have for the CL to be 0 and then negative. Okay. All right. Any questions? Yeah. So these are basically some simple questions related to stability, and we'll exercise this a little bit more later when we get to the project part, because you have to analyze the stability of airplanes using these simple principles, but operating on multiple aerodynamic surfaces like wings and tails and things like that. Okay, so today we're just going to go so far, and we'll continue on that topic later. So today I want to start by looking at boundary layers. So that is continuing our journey of zooming in from far away from the airplane to closer to the airplane in the length scale of the span, and then we further zoomed in into the length scale of the chord, right, looking at airfoils. So today we're going to continue that zooming in process and look at viscous flow and boundary layers. So boundary layers are most obviously important when we get to stall, right? We have been looking at CL is being proportional to like DCL, d alpha is equal to 2 pi, right? That's according to thin airfoil theory. And if that stays true for arbitrary angle of attack, then we could get arbitrarily high CL. That is obviously not correct, right? So a CL, even for high lift airfoils with a lot of tricks like flaps and slats and things like that, can get, it's very hard to get above 2, right? Like you need like modern airplanes during takeoff and landing conditions can get to a CL of 2.2, 2.3, but very hard to go anywhere beyond that. And the reason for that is stall. So this is an airplane model in incipient stall. So you can already see that most of the wing, it's still, the flow still goes from leading edge to trailing edge, but there are very strange patterns appearing starting from the root, right? So this is a visualization of what is the direction of airflow very close to the surface. So, and colored by how fast that flow is. So what you see is that the speed is still pretty normal on the outboard, but inboard you see the flow goes in strange directions, and that basically indicates that this part of the wing is already stalled. So today we're going to start zooming into the boundary layer and look at why stall happens, and what can we do to predict a possibility of stall based on the geometry of the airfoil. Okay, so that is a very relatively long route. So we are first going to look at the boundary layers without the influence of pressure, which means looking at the boundary layer on a relatively flat geometry, right? Okay, so to do that, we first have to think about what forces affect the boundary layer. So here is a very distorted view of the boundary layer. I'm saying distorted because what this picture does is it magnifies the vertical axis and shrinks the horizontal axis. Normally, we know that the boundary layer is very thin, right? Which means that the thickness of the boundary layer is going to be very small compared to the axial length of the geometry, right? So this is a magnification so that we can actually look at it more carefully. Okay, so when we previously look at inviscid flow, we have actually considered only one type of force that is acting on the flow, right? Remember when we derived Bernoulli's equation, what is the only force we are considering? Pressure, right? And we have derived what is the pressure force? Let's say pressure force per unit volume. Do you remember what is the pressure force per unit volume of fluid? Again, I think we derived that by considering a box of fluid, right? So let's say a box of fluid, and on the left hand side is high pressure, and on the right hand side is low pressure, right? And the surface area is S, and that's also S, and the distance between the high pressure and low pressure regions is D, right? So what is the total amount of pressure force on this volume? Right, so the total amount of pressure is actually the pressure on the high pressure side times S minus the pressure on the low pressure side times S, right? So that's delta P times S. That's the amount of pressure force. And in order to derive the pressure force per volume, I need to divide it by the volume, which is S times D, right? That gives me delta P over D, right? And in a small volume, that's actually the gradient of pressure, right? And the force is negative. It points towards the direction of lower pressure. Okay, so we're still going to consider that in the boundary layer. But in the boundary layer, there is an additional force we have to consider. That's the topic of this module, viscous force, right? So that's pressure force. And the viscous force is the topic of this lecture. Okay, so the topic of how big is the viscous force is actually in general quite complicated. So today we're not going to go into the complication of deriving how much is the viscous force in the general flow. So we are only going to focus on parallel shear flow. So a parallel shear flow is basically a flow where the velocity is aligned with a certain direction, with a particular direction. Let's just imagine that direction as x-axis. So that's the x-axis, and the flow goes in just that direction. But the velocity magnitude, the direction is the same, but the magnitude actually depends on y. So basically y is equal to uz is equal to 0, but ux is going to be a function of y only. So that's the simplest setting in a viscous flow. Okay, so first of all, let's just point out straight that this flow has no way of satisfying the Bernoulli's equation. Why is that? Okay, it's because, well, if you want Bernoulli's equation, you have to involve pressure, right? Okay, now if you think about the pressure, if the flow goes straight, if the flow doesn't turn at all, is it possible there is any pressure gradient in the vertical direction? No, right? Because if there is a pressure gradient, the flow is going to turn, right? So if it goes straight, then there is no pressure gradient. And if there is no pressure gradient, that means P is a constant, right? Okay, there is no pressure gradient in this direction, and the U is not a function of X, which means the flow doesn't accelerate or decelerate. That also means pressure is not a function of X. So pressure in this parallel shear flow is a constant, no matter what X, Y, Z is. But the velocity magnitude is not constant, it's a function of y, right? So if you add the P with half of rho V squared, it's not going to be a constant. So Bernoulli doesn't work. And of course, the reason is that vorticity is not going to be 0, right? And what is vorticity in this flow? Omega. In this case, we only have one component, that is dux, dy, right? So it's going to be, actually in this case, it's going to be negative of dux, dy, and I can just write this not as a partial derivative, but as a total derivative, because my ux only depends on y. So as long as ux is not a constant everywhere, my omega vorticity is not going to be 0. Okay, and that's an indication of Bernoulli doesn't work. So let me just state what is the viscous force acting in this flow. So viscous force, I'm going to write it down as tau. Tau is equal to the viscosity times the derivative of u with respect to y. Okay, so that's a force acting between two layers of fluid. Okay, so let's just imagine if I draw a control volume on a particular layer of fluid, draw a rectangular control volume. Okay, and here, to understand the viscous force, let's imagine, let's focus on two planes, the lower side and the upper side of this control volume. On the lower side, what is the viscous force acting on the control volume? The viscous force can be imagined as a friction, right? There are two ways to think about viscous force. One way is to think about it as a friction. The fluid on the outside of the control volume is moving slower, right? And in the control volume is moving faster. So if you think about these two layers of fluid as two layers of solid, and they have a relative velocity with each other, the flow below is moving slower. What is the slower moving fluid? A drag or friction that's acting on the control volume. Which direction is going to be the force? Yeah, upstream, right? It's slow because the flow outside is moving slower. The slower fluid is going to decelerate. It's going to drag it back, right? So that tau is going to be dux, dy acting in this direction, right? And contrary at the same time, the flow in the control volume is going to drag the flow underneath it with the same viscous force in the downstream direction. So similarly, there is also a viscous force acting on the upper side that is accelerating the flow. That's also dux dy. So these two forces would only not cancel each other if the derivatives of the velocity above and below the control volume are not the same, right? So if you get a constant gradient of velocity, then the viscous force would exactly balance each other, right? Okay, so that's the reason that if you think about the viscous force, so this is the viscous force per area, right? Or called the viscous stress, right? Force per unit area is called the stress. So think about the viscous force is a force that acts in a perpendicular direction as the pressure force. So if you have a face that's facing up or facing down, any pressure force would actually point up or down. But viscous force works in the perpendicular direction. It is working in the direction that's parallel to these surfaces. All right. Okay. So now think about what is the viscous force per unit volume so that we can make it compatible with the pressure force. So the viscous force per volume is going to be the difference between the viscous force on the up and down of this control volume, right? So that would be a delta tau. So delta tau times the surface divided by the volume. So that would be basically mu times du dx du dy at the upper side minus mu times du dy at the lower side divided by the volume, right? And the volume is equal to the surface area of this times the delta y, right? So that's surface area times delta y. And on top, we are also multiplying by a surface. So if we cancel the surface, that's basically a delta of, and if mu is constant, we can move mu out. So it's a delta of dux dy divided by delta y, right? So it's how fast does the velocity gradient change as a function of y. In other words, right, it's a derivative of the derivative, or a second order derivative, right? So that's mu times the second derivative of Vx. Okay, any questions on this? All right. Now let's actually use these two. Let's actually start to use these two facts. The pressure per unit volume is minus grad P, and the viscous force per unit volume is viscosity times the second derivative of velocity, right? And try to figure out what is the relative magnitude of these two forces, and in what condition would the pressure force be much greater than viscous force, and in what condition would the viscous force be much greater than pressure force. Okay, so let's just think about what scenario, right, would the pressure force, which actually let's just imagine if I have flow going from upstream to some downstream location. Okay, and we derived the Bernoulli's equation by saying that, okay, so the u times du dx plus dp dx is equal to a constant, right? Is equal to 0. That gives me, and I have rho here, that gives me a Bernoulli's equation, right? But in this case, we also have a viscous force over here. So let's add the viscous force times the derivative of second derivative velocity with respect to y here. Okay, and I should actually make the left-hand side all partial derivatives because now my velocity is a function of x and y. Okay, so now let's actually start to look at the order of magnitude of these two terms. So in the first term, if my pressure changes sufficiently, if I have enough pressure gradient to significantly alter my velocity, right, over a length scale of delta x. So let's say here I have a length scale of delta x. Then the left-hand side, the combined left-hand side, actually we know that has an order of magnitude of half of, let me just ignore the half because I'm looking at order of magnitude here, rho u infinity squared, right? Okay, and I'm looking at the change of rho infinity squared. So that is the magnitude of both the first term and the second term before I divide it by delta x. So if I look at the change of both terms, then I have a delta x over in the first term. So that's the magnitude of the relative both terms in the left-hand side. And on the right-hand side, I have viscosity times the u infinity, not square, but divided by delta y squared, right? Okay, so basically what I'm saying is that I have two terms on the left-hand side that are both of order of magnitude of delta u, rho infinity squared divided by delta x, and that is equal to the right-hand side. And now I need to determine, is the right-hand side small relative to these two terms? And if that is small, then I can approximately say that the summation of the left-hand side two terms is equal to 0 and still apply, and which means my Bernoulli's equation is still going to be approximately true, right? On the other hand, if the right-hand side has an order of magnitude that's close to the order of magnitude of the individual terms on the left-hand side, then we can no longer say that the left-hand side actually adds to approximately 0 and use Bernoulli's anymore, right? So the magnitude of this and this, the relative magnitude, actually tells me that how approximately true is going to be Bernoulli's equation. All right. So let's actually divide the left-hand side by the right-hand side to get the relative magnitude. The relative magnitude is going to be rho u infinity square delta x divided by mu u infinity delta y squared, which is going to be rho u infinity, so one of these cancel out, divided by mu, and then I have delta y squared over delta x. All right. Okay. So if this number is much greater than 1, then what I can say is that in this blue equation, the right-hand side is negligible compared to the left-hand side terms. And the Bernoulli's is approximately true. Okay, but if that ratio is not much greater than 1, then I cannot neglect the effect of the right hand side in this equation, and the Bernoulli's is no longer true. All right. Okay, so that means whether this number is much greater than 1 actually matters a lot. So let me actually rewrite this condition in some other forms. The first form I'm going to write is delta y over delta x. The delta y over delta x is much bigger than 1 over, then actually mu over rho u infinity delta y. So that's the first form I'm going to rewrite this. And the second form I'm going to rewrite this is delta y over delta x squared is much greater than mu over rho u infinity delta x. Okay, both are equivalent, right? I'm just multiplying another delta y over delta x on the left-hand side to get this. And this is the condition over which you can approximately use Bernoulli's equation, right? Which means the stagnation pressure is approximately constant. Yes?
That Reynolds number.
Yes. So on the right-hand side, this is exactly the definition of the reciprocal of the Reynolds number. So this is the Reynolds number defined in terms of delta y, and this is the Reynolds number that's defined in terms of delta x. Right? The Reynolds number is density times velocity times a certain length scale divided by viscosity. So that's the definition of Reynolds number in general, right? So Reynolds number defined with respect to a certain length is defined as rho u l divided rho and divided by the viscosity. And if you choose different characteristic lengths, you get different Reynolds numbers. Okay. And in particular, the second equation is very useful because we usually have a good characteristic. So we usually don't know, right? In the beginning, let's say we only have an airfoil, a wing. We don't know what is the thickness of the boundary layer yet, right? So it's better to use this equation. That gives me, for what delta y, what is the scale in the y direction or the wall normal direction? Can I ignore the effect of viscosity? Right? So if I'm looking at a length scale, delta y, much greater than the square root of 1 over Reynolds number with respect to the chord length, right? I can use delta x as a fraction of the chord length. Or let me just write it down again, right? So if I'm looking at delta y, that's much greater than delta x can be a fraction of the chord length. So let me just write c, 1 over re with respect to the chord length, square root, right? So that's using the second equation, delta x, by choosing delta x equal to like on the order of the chord length. Then I can approximate the flow on that scale as inviscid. Inviscid assumption is okay. And if delta y is not much greater than that, but is several times or on the order of that number, then I cannot approximate the flow as inviscid, and I'm looking at a scale of the boundary layer, right? So this actually gives me what roughly the thickness of the boundary layer is. Yes?
When you're talking about delta y, you always mean delta y like from the surface up to some value of y, or
Yes, right. So basically, from this analysis, this just tells me that if the velocity varies across a scale of delta y, right, then I can no longer assume Bernoulli's is true, right? In the actual boundary layer, the velocity varies significantly across a shear layer near the wall, right? So if the boundary layer stays attached, doesn't separate, then this delta y indicates a length scale from the surface. All right. Okay, so this is an analysis that tells me what is the scale we are looking at when we analyze the boundary layer. Yes? How much bigger is much, much bigger? That's a very good question. So in reality, it actually depends on the pressure gradient, as we are going to look at later. But for flat plate, if this is about like 5-6 times larger than this, the flow is basically inviscid. So we're going to look at in the next lecture the influence of pressure gradient, and that actually gives us the factor is actually going to change depend on the shape of the boundary layer. So we're going to look at that later. But okay, so yeah, so in this lecture, let's actually start. We have a qualitative analysis, right? The order of magnitude. So let's actually start getting to the quantitative analysis of a boundary layer. So that is starts to look at the boundary layer and apply an exact conservation of mass and conservation of momentum argument on the boundary layer. So first of all, let's to get started, let's assume the boundary layer has a velocity that varies from 0 velocity to the free stream velocity at a certain delta, right? So let's call the delta the boundary layer thickness for now. And the friction on the wall in force per area is exactly the shear stress, the viscous shear stress we talked about on the last slide. That's the viscosity times the gradient of velocity, which in this case, in this simplified case, is V infinity divided by delta, right? So that's the force on the wall. Okay, so first question is how much flow crosses this cross section, right? This cross section from the wall to a height of delta in which the velocity varies times a span, right? So the span is going to be in the direction normal to the screen. Okay, how much mass flows across that area per second? How do you compute mass flow per second? Yeah.
Integral rho area.
Yes, integral of rho times what?
Oh,
Velocity, right? And the area. And the area in this case is dy times a b, right? B is going to be the span direction. Okay, so that's an integral over the surface. Let me just integral of surface rho u ds is equal to that. Okay, and in this case, u is a linear function of y, right? So we get a b, and the rho is a constant, and u infinity times y over delta dy, integration from 0 to delta, right? From 0 to delta, and that gives me, because of the linearity, right? The integral is just the middle of 0 to u infinity. Is actually half is going to be b times rho times half of u infinity times delta, right? Agreed? Right, it's like I'm taking half of the v infinity over here, right, and rho half of infinity times the area, which is b times delta, right? Okay, now the question is, what is the height of the stream tube with the same mass flux at x equal to 0? So because all of this mass flux has to come from somewhere, right? So if I draw a stream tube, what is the height of the stream tube at x equal to 0 before the boundary layer forms?
Again, what do you mean by stream tube?
The stream tube means if I draw a tube over here, then there is no mass flowing either out or into the stream tube, right? A stream tube is bounded by streamlines, which means there is no mass flux in or out. Of course, there is also no mass flux in or out of the wall, right? So that means the mass flux out has to be equal to the mass flux in. Well, the mass flux in is also integral of rho v ds, but the flow is uniform upstream, right? So u is u infinity, right? That means it's rho u infinity times the area of over here, which is b times the height, right? And that height is equal to that. So it's equal to b rho u infinity over 2 delta. So that means h is equal to what? Yeah, half of delta, right? Okay, so that means the stream tube has expanded by a factor of 2 as you go from upstream to downstream. And finally, the final question is, what is the displacement of a streamline by the boundary layer? So this streamline, right, as I said, the stream tube is bounded by a streamline. It's going to be displaced all the way from half of delta all the way to delta downstream. And so does every streamline outside the boundary layer, right? Because the flow is u infinity and u infinity outside the boundary layer. So that's our starting analysis on the quantitative analysis of a boundary layer. And we're going to continue in the next lecture, not just looking at the mass balance, but also momentum balance, and starts to define the different thicknesses of boundary layers. All right, so see you on Friday.